So how did we do the detection or estimation of the flow? The first thing we had to figure out was how we can separate between the different states that we get in a tank. And there are four basic states that we see. There's outflowing, there's not flowing, then there's filling, and there's transferring. So the transferring was an interesting one because it can actually move between the two tanks. So there's no net flow, but there is obviously a change in level. The filling one, the fills can happen when the tank is not flowing or when it's flowing as well. So here's an example from the demulsifier tank. You can see in this state here, we've got the tank B is flowing. The blue line is decreasing smoothly. The A tank is not flowing, it's stable. Then we get a period where B stops flowing and A starts flowing, and then there's a fill, and they're both filled. B is filled while it's not flowing, A is filled while it is flowing. Then we get a period where some is transferred out of B back into A. In fact, it happens twice. So we get a simultaneous transfer in, transfer out event as well. Demulsifier tanks. There we are. This is the real trend of the level. And you can see our calculation of the demulsifier rate. But importantly, we are ignoring the tank fills. So we've been able to determine the difference in the state. We're ignoring the tank fills, and we're also ignoring the tank transfer events. So if we zoom in on this area here, zoom in here, you can see we've got a transfer event, but the flow is staying nice and stable. Now, in the old method, that would have caused a flow spike, but we're able to iron these out. In order to determine these, we're using standard deviation. So I'm going to take you briefly through how we do that for one of the tanks. But what the aim is to try and find a time period over which the standard deviation the difference is enough for us to determine the difference in states. So for the demulsifier tanks, here we can see when the standard deviation is below 0.07, we're not flowing. If it's greater than 1, we're filling. And if it's greater than 0.07, then we're in a flowing state. So let's have a look at how we do that for a real tank. Let's take a clean trend here with a level on it. We're using the H2S remover because it's one of the most stable. It's pretty nice. So if I right click on the trend, I can quickly add a standard deviation. That has I'll put it on the right hand axis so we can see it a bit more easily. And let's change the color. Okay. And let's zoom this in a bit so it's easier to see. So here we can see that we've got quite nice separation already, almost. This is such a clean level that we've really got no problem seeing the difference. But by default, this has added a 10-minute standard deviation. So we could say we can tell the difference on this tank easily with a standard deviation of 10 minutes. In reality, if I zoom in on the level on this tank, we actually see quite a lot of variability. So in practice, it wouldn't work to just take 10 minutes, but we can increase it. So we could increase it to say 1 hour. There, and there we get very nice separation between the different states. We can clearly see that when it's not flowing, it's nice and stable. We see very little change. When it is flowing, we get a big standard deviation. And when we have a fill, we get a big spike. Another thing that we can do is add a difference calculation. So let's, the quickest way for me to do that is to add a standard deviation and change it to a diff. I'm going to do my diff over 1 hour as well. There's my difference, and you can see when we have flowing states, we have a nice big separation between the difference, and when it's stable, we're getting very little difference. So this is a nice tank example. This is pretty straightforward, but it shows the principles that we're using to do this. So we can make a truth table. for the different states. What we see is that if we get a gradient that's equal to or greater than 0, then we're definitely not flowing. If the standard deviation is less than 0.0 and the gradient is equal to or greater than 0, we're not flowing. If the standard deviation is greater than 0.07, and what you'll see when we deal with blips is we may be seeing a big variation in the gradient as well. We could be possibly flowing in both those scenarios. If the standard deviation is greater than 0.05, we could be in an unstable period if the gradient is greater than or equal to 0. If the gradient's less than 0, we're probably flowing. And if the if the standard deviation is greater than 1 and the gradient is greater than 0, we're definitely filling. If the gradient is less than 0, it's some unstable period. We've obviously got a lot of variability, but a periodic negative gradient. So we have some instances where the tanks are much, much less stable. And we then have things like this, where we see a big variability in the standard deviation. And it's quite difficult to separate the regimes at times. And so in this instance, this is on the downhole corrosion inhibitor, one of the more unstable tanks. We have a case here where the standard deviation is much higher when the tank is actually not flowing because we've got a big variability in the level. So we also need to use the difference to try and determine if this tank is flowing or not. So here's an example here where we have a tank is flowing. It's evenly flowing. As a human, you can tell this by eye, but what we see is the standard deviation has gone up, but also there's a big variability in the difference as well. And actually, if you zoom in on this, at times we see that the difference went positive. And so if you just looked at the gradient, you would say it's not flowing. And we have to deal with that to know what to do. That's the basis of how we've determined the different states. And what I'm going to talk about next is how we've then used that to build an algorithm. And the platform we've used is called Node-RED. And we'll look at how we've built an algorithm to determine a trusted tank flow. So we've used a platform called Node-RED, which is a low-code scripting platform that enables you to drag and drop things. It's great because you can also add scheduled execution to things. You can do things like persisting variables. So that's important to us because we can remember a previous state. We can use it to write back to time series data, and we can rerun stuff so we can backfill data when we're happy with the algorithm. And we can also create endpoints like APIs that can be consumed by other data sources. And for someone like me, this is great because I used to do a lot of VBA programming in Excel, and this is just like that. But even better, it's centralized, it's secure, and it's even more powerful actually than Excel VBA. I think this is a game changer because it enables us to build things much quicker and cheaper than we could if we were writing code for it. So let's have a quick look at the platform. This is Node-RED, and you can see it running to the side. This is it running every 5 minutes to calculate the tank levels. Here we've got the main algorithm that's doing the tank calculation. To this side here, we have the same algorithm, but that we can run manually with a pre-configured period and maybe a selection of tanks. We can run a backfill. And then we've got some tools where we can reset persistent variables and things. This is the algorithm that does the code. The point to take from this is all of the code is about the functionality of calculating the tank flow. We don't have to do anything about setting up an app, setting up a framework, doing security, scheduling it. It's all handled. And then we can see here configurations and things within it. So let's just take you through a few points. There's two algorithms that we've done. I've talked about, we've estimated the flows, we've detected fills. The flip fills one is on another tab. We're not going to look at it today, but do email me if you want to know how we did that. The key features of the script that we'll go through is that now we do nothing based on just one data point. The previous calculations had to run in real time. They had to take the latest data and work out based on at runtime what was going on. Now we can remember the previous state and we can do things like build evidence. Like, do we think that the flow state has changed? Are we confident? If so, we'll use a new value. So we have this idea of a confidence. So something that the state has to be changed for at least 10 cycles before we believe it's true. So if we think a tank's flowing, we put 1 in the confidence pot. If the next time we come around, we still think it's flowing, it becomes 2. And when it gets to 10, then we say, okay, we're confident it's flowing. Now let's look at what we think the flow is. So we have this idea of confidence and also the last trusted flow. So we hold a value that we say, this is what we think is the trusted value, and we calculate a new value every cycle. And we decide if we're confident enough in the new value before it becomes the trusted value. So in order to do this, every tank now has a set of parameters with it. First of all, it's got the input level transmitter. That's the basis for everything. And we also need to know the tank volume. Then these parameters come from the trends I showed you before, some analysis and tuning. We need to know the stability threshold. What do we think the standard deviation needs to be above before we can say for sure it's flowing? And we need to know the period that that standard deviation is taken over. So we have the idea of a period as well. We need a gradient threshold. So we need to say, if you see that it's downward sloping, it needs to be at least below a certain level before we'll believe it's flowing. And to stop some craziness happening, we need to know a minimum flow and a maximum flow. If for whatever reason we should get some funny numbers, we need to limit the average, for example, from going very high, because that will be hard to get back from. And we have a default flow for when we initialize things, or like a get out of jail card. If something goes wrong, return to the default flow and try again. And we've also got these new outputs. So we write this data back into tags so we can trend it. And you saw that earlier when I pulled it up with Marguerite. We're writing both the estimated flow plus the average flow. And we can calculate a difference flow, which is the instantaneous as well. So there's a few points that have helped us smooth out some of the blips. As soon as we see that the tank starts flowing, we use the last trusted flow rate. We start calculating the average once the tank has been consistently flowing for 10 cycles. If we believe if the tank has flowed consistently for these 10 cycles plus the stability period, we will believe the average now that we've been calculating. So this avoids any short-term, any averages based on a like 10-minute reading, which could be very steep. We at least wait for 50 minutes plus the stability period. So we get a decent sample to take it across. We build up the average for 8 hours or 4 times the stability period. The reason is 8 hours should be enough to have a decent change in level, but we originally were thinking, let's keep building up the average forever. But that means we don't see changes in flow. So we now have a sliding window that goes up to a maximum of 8 hours. The bigger the window, obviously, the slower we are. And we've got ways of dealing with blips. So if we see that the standard deviation has gone high and the gradient's gone high, we literally put a pause. We say, don't change anything, just keep the trusted flow until we're certain that we've either changed state or we are actually still flowing. This was an example of a blip, and you can see here the blue line that the flow is actually pretty smooth. So although we saw very high variability, and it lasted for a long time, we're looking at 8 hours of variability, but the flow remained pretty stable throughout because we were able to say, just keep the trusted flow. And during this little blip, actually, what we saw was the gradient went positive. If you took any 2-hour period within this blip, there were points when we saw the gradient going positive, but the tank was actually still outflowing. But I think this is one of the benefits of being able to have the algorithm. We could have these like multiple different factors that had to come together. And there's the piece of the code that did it. So we don't, every time we see a period of instability, all we do is take one off the confidence. When it's flowing, we say, oh, we've got a confidence of 10, it's flowing. If we see a period of instability, we take one off that. We say, okay, we've gone back down to 9. We see it again, we're down to 8, and it has to recover back to 10 before we start recalculating the average again. Okay, and that's the results that we saw again previously. Much more stable. I'll briefly let go through this the node-RED stuff. You can see the configuration of parameters that I mentioned earlier. And then we've got code that most of you will recognize if you can do VBA. We've got for loops, declaring constants, Boolean checks for things. We've got loops or statements. We create little output strings that we then push to an API to write. The bulk of the, oh, I think this is the backfill. Oh, no. Here's the bulk of the code that does it. We have, first of all, a check where we think it's flowing or not. We say, do we think the tank's flowing? And that gives us a 1 or a 0. But then separately, we look at what we think the flow is. And then we use the flowing status to mask it. So we don't necessarily do everything in the straight order. This is thanks to Ben Hickey, one of the engineers in Eigen. Really nice way of doing it, splitting out the determination of a flowing state from what we think the actual flow is. And then we've got various checks to go through and decide, are we in a stable period? Have we got some spiky weirdness going on in it? Stuff like that. If anyone's interested in the detail of this, call me. I'm very happy to go through it. I've loved this because I've been able to help tune this and spend time on it, whereas previously, when it was all done in code, it was impossible, really. Because it's all through a user interface, it's been easy for me to understand what's going on and to have input to it and to help tune it from an engineering point of view.